Hello, this is a small video to be the third in a series of 3 videos based around electrical protection. It is to serve as a form of podcast rather than a visual experience, and it is going in an order which I will briefly explain now. So, skimming through all of the slides to our next slide, it is understanding protection schemes. So I've gone over circuit breakers, CBs for short, fuses, relays, VTs, and CTs, albeit not in extreme detail, not with any calculations. That will be for a separate video if required. And the usage of such components is paramount, as with the combination of such, the downstream loads, whether it be critical infrastructure or even non-essential equipment, either way, they will be protected. And as such, we need to have schemes in place for this. So we first have the overcurrent protection scheme. And what this is an ability to sense an excessive current, whether it's a short circuit or an overload, and be able to, in a timely manner, disconnect the circuit from which the overcurrent is occurring and prevent fire and damage to equipment, or even in the worst cases, harm to people, which will take the most precedence naturally. So this happens with the aforementioned overcurrent relay, or even an earth fault relay, but in this case an overcurrent relay, where the excessive current will exceed a threshold over a period of time and cause the associated circuit breaker with that relay to trip. So a short circuit will trip instantaneously, and an overcurrent, depending on the size of the overcurrent, or an overload, will trip after a certain period of time. This will be designed by the person incorporating the scheme. However, there is something called IDMT, so it's inverse definite minimum time. So this basically is a inverse relationship where the size of the current, being large, will produce a smaller trip time. So 10 times current, for example, will cause a much reduced time. The same goes for 3 times current. So, for example, you could have 10 times current in maybe 2 seconds, or it could be 3 times the current in 10 seconds. So you basically have it in such a way that a massive overcurrent will reduce the time it takes for the protection to act. It's used on feeder protection, which is the feeder to, for example, a transformer, to protect the transformer, and also to protect motors. However, each one has different requirements, specifically motors as well, as they do have an inrush current. Fault protection. So let us imagine we are on a construction site. A big digger is going around and it cuts through a cable. Now, that cable is essentially down to earth, resulting in an earth fault current to flow from the phase 1, 2, or 3 down to earth. Each of those are different. A single phase, well, you have different faults basically, which can be explained in a different video. However, let's just focus on phase to earth, where a very large current is going to flow. You'll have an imbalance between the phases. This imbalance is measured by your CT arrangement. So when it's detected, a fault is clear to be on the line that the protection is monitoring. Therefore, it sends a signal to the Earth fault relay and causes it to trip the associated circuit breaker. Another version of this to provide protected zones is restricted air fault, REF, and this can protect transformers. And how it works is that it monitors the current entering and leaving this specific zone, and it ensures that if the sum of the enter and leave current is unequal, then it causes a trip. The zone is then indicated to have a fault within it, and it's used on transformers and generators. Next, we have high-set overcurrent, which is a form of backup protection. So I just explained briefly the overcurrent. So in the event that the overcurrent protection doesn't function, doesn't activate, um, then at a much higher delayed current setting, the high set overcurrent on the primary side of a transformer, whereas the overcurrent, which is the primary protection, would be on the low voltage side of the transformer. This high set overcurrent on the HV side would delay, but as a backup protection in the event of failure. Protect the feeder essentially, and also the transformer, but predominantly the feeder. Next, we have differential protection. This, again, similar to the restricted air fault, measures the current entering and leaving a protected zone, and it detects a fault within the zone. Brilliant. We can then say, right, this zone has a fault within it. It works by measuring the current on the primary and secondary side of transformer, look at the difference, and again, there is a difference. It should sum to zero. Of course, there are three phases. It's used to protect transformers, generators, and bus bars. It's incredibly high speed, and it's quite usefully sensitive to faults specifically within its zone, which then minimizes nuisance tripping because it's not affected by anything outside of the zone, because it's just looking for differences within itself. However, with this, it becomes quite expensive as the resolution rating of the circuit of the current transformer must be quite high, which then drives up the cost. Um, I have also experienced issues in the UK where there are a lot of standard sizes. However, there are some crossovers with designers where they like to use IEEE standards rather than British standards. So that is something to be aware of. Not necessarily something wrong with that, but it is a preference to work to British standards rather than IEEE. However, both are used throughout the world. Distance protection. So this is for a transmission line, which, because of the length of line, will have an impedance to it. So it basically uses the aforementioned combination of a voltage transformer and current transformer to calculate the impedance. And when such a threshold is exceeded, the relay will trip, indicate a fault in a specific zone, and act as either a backup protection, as um, a protection for backup within the same zone or for a different zone. Quite useful. However, one issue with this, because it does rely on the impedance, is that, for example, during summer, the impedance of the line will be different to that in winter. So it can be quite a challenge to make sure that this system appreciates that. So yeah, overall, each type of protection has its own uses. Some systems will use everything, every kind of protection. Some will just have their selection of maybe overcurrent and airflow. But overall, we have overcurrent, detects overloads, short circuits, can be instantaneous depending on the type of fault. If it's a short circuit, we use a distribution and motors. So let's say we want to detect a transformer or a feeder. We then have earth fault, where we detect ground faults very fast. Monitors the three phases or the phase to earth, line to earth. Used for transformers and generators again. And next we have the differential, where we compare the incoming and outgoing current very fast to activate. And again, transformers and generators. We also had the high set overcurrent, which is also backup protection. Secondary protection to act at a slower rate than the low voltage primary protection. Again, stressing at a delayed rate. And finally, as shown on the screen, we have the distance protection, which is used to measure the impedance to the fault. So the speed of operation does vary for this one. As it states on the screen, it can act as a time-delayed backup protection for distant and local faults. For example, if the primary protection of that line weren't to work, it can work for that. Or if there's an extremely far fault, it can act as an even longer delay to trip that. So it is very much so based on the transmission line and the networks surrounding it. So I hope this has been a useful video with not too much rambling. Appreciate there's a lack of pictures, but again, I want it to be something that you can listen to. So thank you very much for listening. And that is part 3 of 3. Thank you and goodbye.